Hi, my name is Felix Meister, and today I'm going to present to you our work on graph convolutional regression of cardiac depolarization from sparse endocardial maps. The presented work is a joint collaboration between the Friedrich Alexander University of Erlangen-Nürnberg, Siemens Healthineers, and the Johns Hopkins University School of Medicine. This work revolves around contact mapping of cardiac activation. Here, a catheter is inserted into the ventricle and measurements of voltage and activation times are acquired. There are few problems with this technique. Since points are being taken sequentially, obtaining high-resolution maps is a time-consuming process. Furthermore, contact mapping, which is commonly performed endocardially, provides only information on the heart's surface and fails to capture the electrophysiology of the complex 3D arrhythmogenic substrate within the myocardium. The goal of this work is to estimate the local activation times in the biventricular domain from a sparse set of endocardial measurements that are acquired during sinus rhythm. The proposed method works as follows. Given magnetic resonance images, the left endocardial contact map, and 12-lead ECG traces, we represent cardiac anatomy as a tetrahedralized mesh. Next, geometric and electrophysiological features are extracted per vertex. The mesh with vertex-wise features is then processed by a graph convolutional neural network to regress local activation times in the entire biventricular domain. A graph convolutional approach was chosen since topology is one of the main determinants of cardiac electrophysiology. It is also expected to provide better runtimes compared to traditional methods such as a computation model personalized to the measured data. For the graph convolution, we use so-called graph stage layers. The basic idea of this approach is to sample and aggregate information over the neighborhood of a vertex. Suppose we have a graph with 4 vertices and a handful of undirected edges. To update vertex 2's representation, the features of its immediate neighborhood are first aggregated, for instance by using the mean function. The resulting neighborhood aggregate as well as the feature of vertex 2 are then passed through a fully connected layer with a nonlinear activation function. To process the whole graph, the same layer and weights are applied to all of the vertices. As input to our network, we use geometric and electrophysiological features. For the geometric features, we represent the vertex position in 3D using local coordinates from a cylindrical coordinate system. It is defined by the left ventricular axis and the apex as origin. In addition to the local coordinates, we denote vertices that belong to the left or right endocardium, the epicardium, scar, and border zone using categorical features. For the electrophysiological features, we use information from the contact map and the 12-lead ECG traces. The measurements of activation times are given on a set of vertices on the endocardium. Since each vertex requires the same number of features, we fill the respective feature with -1 for all vertices without measurements. In total, 24 features per vertex are being used. Putting it all together, the tetrahedralized mesh with vertex-wise features is processed by an adaptation of PointNet, a deep learning framework to process 3D point clouds. At first, local features are extracted using a cascade of 20 graph stage layers. Since each layer is acting on a different receptive field, we concatenate the output of each layer as well as the input features to form the local feature vector. This vector is further processed by a series of fully connected layers with shared weights. Max pooling is applied to extract a global feature vector. Local and global features are combined and processed by another series of fully connected layers with shared weights to regress the local activation times in the entire biventricular domain. To train the network, 2 loss terms were incorporated. First, a weighted mean squared error between the predicted and the ground truth depolarization is applied. Vertices with activation measurements were weighted higher to constrain the network to incorporate the given information. The second loss term is a regularization of the network to match the given QRS duration. The network was trained for 500 epochs using the Adam optimizer with hyperparameters as shown on the right side. As a method of reference, we chose a graph-based computation model of cardiac electrophysiology, which we denote as DenseP. Vertex-wise activation times are computed by the Dijkstra algorithm with edge-wise costs that consider the fiber direction and tissue conductivities. We personalize the model to the sparse measurements using a scheme that is inspired by neural networks. At first, a global optimization of the conductivities for 5 homogeneous regions is performed to match the ground truth ECG. In a second step, the discrepancy at the measurement points is minimized by applying gradient descent optimization. Gradients are first computed at the vertices with measurements, and backpropagation is then applied to obtain gradients for all edges along the paths of wave propagation. The weights are then updated using a gradient descent step. For training and evaluation of our method, 16 swine datasets with MRI, 12-lead ECG, and contact maps were available. Due to the limited amount of data and no ground truth information within the myocardium, we resort to a computation modeling approach. Anatomical variability was increased by sampling over 200 geometries from a statistical shape model, which was built from 11 randomly selected swines. Tetrahedralization and mesh tagging was applied to generate anatomical models, on which we defined a set of 4 initial activation points. To obtain ground truth information, we simulated 50 depolarization patterns per geometry. Hereby, the same graph-based computation model of cardiac electrophysiology was used. In each simulation, the conductivities for the myocardium as well as the left and right Purkinje system were randomized. Furthermore, per simulation, one of the standardized 17 HA segments was set to be either non-conductive scar or slow conductive border zone. In total, over 10,000 simulations were generated. We split the data by geometry into 90% for training and 5% each for validation and testing. We evaluated our approach in 3 different setups of increasing complexity. At first, the network's performance was evaluated on the 5% left-out cases from the synthetic database. To this end, 25% up to 100% of the left endocardial ground truth was provided to the network. We measured the mean absolute error in local activation times for the left ventricular endocardium, the border zone, and the whole heart. A mean absolute error of less than 3 milliseconds was observed over the entire myocardium when providing 25% of the ground truth data. One can also observe that the more data is provided to the network, the lower the errors become. In a second experiment, we applied the network to the 5 unseen swine datasets, which weren't used to generate the statistical shape model. For these datasets, scar and border zone was modeled by segmentations derived from late enhancement MRI. To obtain ground truth information, we used again the graph-based computation model with randomized conductivities. While the errors for the graph convolution network are higher than before, they are comparable to our method of reference with slightly lower errors over the whole heart. DenseP, however, outperforms the network when considering the endocardium. This is not surprising, since the method's optimization paths are along the endocardium. At last, we applied our approach to noisy clinical data for one of the unseen cases. To use the data, we first manually aligned the measurement point cloud to the anatomical model. Nearest neighbor projection is used to map the point cloud to the endocardial surface of the tetrahedral mesh. The objective of this experiment is to use the subsampled endocardial data to recover the high-resolution measurements on the endocardium. In this setup, DenseP is providing very consistent results, irrespective of the subsampling ratio. The graph convolutional network, however, is producing significantly lower errors compared to DenseP when more data is provided. A visual inspection, as seen in the lower right, suggests that the network tends to naively fill in high-frequency data, while DenseP is producing consistent and more physiologically plausible depolarization patterns. With this, I would like to conclude my talk. A graph convolutional approach to obtain local activation times from geometry and sparse endocardial measurements was presented. The approach was trained on synthetic data and achieved a mean absolute error of less than 8 milliseconds over the entire myocardium in all 3 experiments. Compared to the personalized computation model used as reference, the errors are lower over the entire myocardium. Future steps will revolve around improving the accuracy and physical plausibility, for instance by complexifying the training dataset. At last, the application to mapping of ventricular tachycardia is of interest. We hypothesize that the information about the activation of the complex slow conductive pathways within the myocardium may help guide radiofrequency ablation therapy. Thank you very much for your attention.